talk about how NBOT is different. We don't just filter out contaminants, we destroy them. We're safe for the environment, as Dr. Muller will allude to, and our solutions are scalable and configurable. Welcome, everybody. I guess Lance and an audience of one here. So Lance, welcome. Here we're going to talk about NBOT and how we're the PFAS solution powered by nanobubbles. And again, like we talked about with Dr. Muller, a lot of our scientific R&D has been done in conjunction with the National Oceanic and Atmospheric Administration, who Dr. Muller is a director at. Our main problem here when it comes to PFAS, as I'm sure you know, Lance, forever chemicals have caused cancer, deadly diseases, and all across the country and the world since they were created 75 years ago. About a year ago, EPA set new limits on PFAS: 4 parts per trillion, 10 parts per trillion, depending on the length. And of course, tens of thousands of facilities will need to comply here in the next couple of years. And currently, there are no effective destruction solutions. Current options are expensive and they're not truly destructive technologies, right? And so our solution, in partnership with NOAA, we developed the only scalable, efficient, and eco-friendly forever chemical destruction solution using NBOT as the catalyst, and we're capable of destroying 99.995% of PFAS at a fraction of the cost of the existing options. And so why is NBOT needed, right? We talked about how there's lots of filtration solutions out there. But the issue there is they only remove or contain those pollutants. They don't really destroy them. They don't eliminate them, right? Chemical treatments may or may not work, but they're toxic for the environment. And there are other technologies out there, but they're not safe. They're safe, but they're not scalable, right? They might work in a very small lab environment, but when it comes to treating larger and larger bodies of water, physical devices in the water and things like that just don't work. And so that's why we talk about how NBOT is different. We don't just filter out contaminants, we destroy them. We're safe for the environment, as Dr. Muller will allude to, and our solutions are scalable and configurable. We do this through the generation of ozonated nanobubbles. So what this is supercharged oxidation with the power of these things called hydroxyl radicals. I'm not sure how familiar you are with them, but we'll get to those in a second. And why this matters is that it's scalable, eco-friendly, and more effective than filtration or chemical-based treatment solutions in all of science. So ozone has been used for, I would argue, decades in terms of water treatment. But what we claim is that harnessing the power of ozone inside of this thing called a nanobubble, very, very, very small bubble, creates these things called hydroxyl radicals upon their implosion. Dr. Muller, I'll let you add on a little bit of science there.
If you look at this list here, ozone, hydrogen peroxide or peroxides and radicals are second only to fluorine in oxidative power. And fluorine, of course, is the backbone of PFAS, and we're going to come to that in a little bit. But harnessing this power of hydroxy radicals, which are produced in higher numbers upon the implosion of a nanobubble. And so this technology is coupling both a carrier mechanism and a mass transfer into the water that's much more efficient than just bubbling raw ozone.
And Lance, of course, please feel free to ask any questions.
Okay, and just to let you know that, yeah, I have a master's in physics and took plenty of chemistry, and I've been working with water issues and water chemistry now for quite a while. And for 20 years, I was a state specialist in the Wisconsin DNR on the ozone layer up in the atmosphere.
Oh,
I know about ozone.
Yeah.
O3, yeah, O3 is my friend.
But at a high level, right, it's well known in the industry, destroys bacteria, viruses, microorganisms. The main con is the lifespan, right? We've seen facilities at large industrial scales that are using enormous amounts of ozone, but it's got a very short lifespan, right? 20 minutes or we say under 30 minutes to be safe. It's expensive and it's very hard, if not impossible, to treat large bodies of water with just bubbling raw ozone into the water, right? That's where we introduce the concept of nanobubbles of the ozone. But what these bubbles do is they act like a gas and they diffuse throughout the entire body of water for full coverage, right? Due to their size, under 200 nanometers in diameter, there's no rising or bursting. So as a result, you get controlled, efficient ozone delivery. And like we talked about just now, the release of hydroxyl radicals upon their implosion, right?
Okay, just a second.
Sure.
So how, I guess a technical question. So you're basically injecting ozone, O3, as a tiny, tiny, some way you're able to get it into these tiny bubbles. Are there other chemicals in it, or is it just tiny bubbles of ozone?
Tiny bubbles of ozone, but there's a little bit more to it. Dr. Mully, you can probably
Sure.
talk about maybe the
There's
breakdown and
sure.
in addition to oxygen.
There's a little
Yeah.
bit of oxygen in present, but the advantage here is that when Nathan was talking about ozone, and you well know this, the half life is about 20 minutes. The catch is that the half life of ozone impregnated in a bubble is unknown, because the breakdown of ozone in an environment of ozone is ozone. It just keeps breaking back down to itself. And so the advantage to these nanobubbles is that it keeps ozone in the water. The PAC rim countries are reporting a month. In my laboratory, we see continual ozone presence when we turn the machine off after generating these bubbles for about 10 days. So you've got this extended presence of ozone in the water as these bubbles slowly decompose.
Wow.
Um,
So you're so the in that kind of a situation, in a laboratory situation, you're talking about that 10 days in a pure water or a contaminated water situation.
that's a really good
Good
question. In the
question.
lab, I reported my first 10 days in very clean water, DI water. However, we have taken river water, and I use nuclear magnetic resonance to monitor hydroxy radical production. We were still picking it up in dirty river water after about 7 days. So it is water dependent. However, I certainly wouldn't claim that you're going to have nanobubbles existing. And I think the picture he showed you earlier was with a hog lagoon that we cleaned up. We're working on those nanobubbles weren't lasting very long. There was so much stuff in that water that was sucking. Oh, by the way, the nanobubbles do carry a partial charge, so they are attracted to a lot of things in the water as well.
Okay, and that's really why I said that, because as I imagine ozone nanobubbles are just ozone itself in the water. It's continuously reacting with not just the water but everything else that's in there.
Correct.
And so I would think that the ozone itself, there wouldn't be much of a concentration of ozone in very contaminated water for very long.
No.
But you're saying the nanobubbles are active for up to 10 days. So as a bubble, it's kind of an isolating itself.
Well, the nanobubbles are really quite unique because they. I'm glad you had the physics background, because although the bubbles themselves are not a gas, they behave like a gas. They follow the Henry Boyle's Marriott gas laws. They
Wow.
diffuse, they perfuse, they kinetic Brownian motion, and so they spread throughout. They'll fill the given. They'll fill the given space provided to them. And so as they implode, they're cleaning up, as Nathan said earlier, the entire water column by releasing ozone locally. And one of the things that we're working on right now is this attractive charge, because we think that they actually come up to chemicals due to their electrochemical potential, as well as organisms, algae. I'm a big into cleaning up algae and algae toxins, and they destroy those very easily because they target what they're after.
Okay, that's exactly what I was thinking. That's exactly what I was thinking. If you're talking about nanobubbles, maybe they are actually going to stick to things
Sure.
like very tiny things, not just molecules, but other small things in there, and interact with them. Psh, I would say killing off a bacteria pretty quickly, right?
Yes, we can kill back. In fact, you've been in water, so one of the things, again, we just published this. We found out that bubbling raw ozone in the water, we can take water up to 20 parts per million and not kill all the bacteria, which surprised me. That's a ton of ozone. The minute we turn on about zero point 0.1 part per million ozone in nanobubbles, we'll wipe that bacteria out, and that water will be active for about 7 to 10 days. It'll be that active.
That is an amazing kind of a thing. It's a kind of almost a new state in a way. Uh,
Well, the big thing for from the industrial perspective is that your mass transfer into the water column is so much less expensive
yeah.
because you're not wasting the ozone otherwise.
What kind
Okay.
of efficiency do you have the same maintain the efficiency throughout that 7 to 10 day period, or is there some drop off?
Oh, well, it slowly drops. I mean, there's a calculation on a given body of water that would determine how fast these bubbles are
Mhm.
imploding, and that's going to depend on what's in the water, the ionicity of the water. It works in salt water and fresh water, but it does work much more quickly, it appears, in salt water. And there's a lot of things that go on. So to answer your question, we would have to assess this more specifically for each body of water depending on its own characteristics. But in general, um, we're seeing a minimum of 3 to 4 days of ozone being present in our public water, open water.
How big are these things? If you got a physical size, or
Yes.
how many moles of ozone, or what?
Well, I can let Nathan describe there's intellectual property involved in this, but
Oh,
each
sure,
machine
sure. I'm just wondering
sure,
how tiny they are.
they're less than 5
Yeah.
micron.
Okay.
If you generate a 5 micron bubble and you put it into water, it'll decompress and it'll become a nano. It'll be getting into the nanomolar or meter scale. So they
Okay.
are nanobubbles by the time they make. They're in the water for very long.
Yep. The technical definition of a nanobubble, Lance, unless you may not know, but 200 nanometers is sort of the bridge that I'll say the inflection point between technically a nanobubble to a microbubble. That's a very, very, very small number and very, very, very difficult to measure, of course, on a large scale. So Dr. Mullen and I talk about that all the time. We do have data that shows a quantity of those nanobubbles present in water. Of course, when you get down to that level, it's even,
Yeah, you gotta be
64,
you gotta be
64,
sophisticated on that one.
oh yeah,
For
64
sure.
million nanobubbles fit into one microbubble.
Getting small.
yeah.
All right. All right. Well, that gives me a better idea. But go ahead with your presentation because it may cover some of the questions I'm coming up with.
Perfect. Yeah, no, good questions. We've talked about hydroxyradicals quite a bit here. I'm not sure if there's anything else to add here
So
specifically.
I'd like to go ahead and explain what it's saying here.
Yeah, absolutely. Just like Dr. Muller's described, hydroxyradicals, one of the most powerful oxidants known to science, right? So compared to chlorine, it's up to 100,000 times stronger than chlorine. And that's mostly due to its indiscriminate nature, right? We've used that word quite a bit here today. Indiscriminately destroys contaminants. And it works exponentially faster and, just like Dr. Muller just said, more cost effectively than traditional chemical treatments.
Just one thing I'll add to that is that the hydroxy radicals, what's so useful for them is that they're so powerful that it doesn't matter if the chemical is dissolved, if you've got a contaminant in the water, or if the chemical is part of an organism, it's going to destroy them both using the same chemistry.
Oxidation.
Yep.
Correct.
Okay.
We've talked about this a little bit, but now let's get to how does NBOT actually work, right? And so we're a pump and pipe based system based on pressure differentials and a nozzle based system. We intake water first, right? So contaminated water will enter our system. We'll infuse this water with ozone, nothing new or too special here. The power of this technology is in its nanobubble generation, right? And so trillions of these ozonated nanobubbles will be ejected from our system. And then this output, right, NBOT, we're sending these ozonated nanobubbles back out into the water column. And so what is important here, and I don't know if we've emphasized it enough, is that we don't treat water when it's in the system, right? We're not generating these bubbles inside of a very small system and then treating it and then sending clean water out, right? We're using these nanobubbles as sort of our worker bees, right? We're taking contaminated water and we're sending these bubbles back out into that water column. Some of that destruction, some of that oxidation is happening immediately, right? Some of it is taking days, but that's really the power of the system. Of course, depends on a lot of different things, right? Salinity, temperature, water composition, all those kinds of things, right? And again, everything up until this point is NBOT only, right? And so pure NBOT, and so Dr. Muller's big focus has been in algae remediation. We've seen enormous success in that area. But of course, we're focused a bit on PFAS here.
So my question at that point is, I don't know if it says what your next slide says, but you're basically using a system just like injecting a chemical into a body of water. You're basically using this to inject the nanobubbles into a body of water.
In plain English, yes, we're taking contaminated water in. We are infusing ozone and generating our bubbles, and then we're sending that water back out.
So I see. So you are running it through a system that infuses the water with the nanobubbles and releases it back into
Correct.
back into a secondary system or back into another.
You can go right back into the
I'm
lake.
trying to understand, if you got one pond here and you got the NBOT system here, and then it pushes it into another pond or something like that.
That's, yeah, good question, Lance. That's when it comes into, I mean, application engineering, right? If you're dealing with a centralized a container or lagoon or something like that, then this can be recirculating in that same body of water, right? If your application is you have a contaminated section over here and you have a clean section over here, and that's the desire is to take contaminated water and send out nanobubble infused water into a new area, that is an option too. Our bread and butter has been pulling out and sending back in ozonated
Okay.
water.
Yeah, and as you explain a couple of the systems, that's what I'd like to see
Yeah.
how they
Yeah.
work.
Anything to add there, Dr. Muller?
Not really. No, you've got covered most of that
Perfect.
as well as I would.
Perfect. Oh, there we go. All right. Again, to this point, everything up until this point has been NBOT only, right? And so back a few slides, we saw that the hydroxyl radical is one of the most powerful oxidative, um, uh, sorry, not a chemical. Help me out, Dr. Muller. I'm sorry.
Sir, what are you looking for?
Hydroxyl radical is the second most
Oh, it's the second
oxidative.
most powerful, second only to fluorine as an
There we go.
oxidant.
Second, exactly, to fluorine. And so bridging that gap between the power of a hydroxyl radical and that CF bond in a PFAS molecule was really what aided Dr. Muller here for, I guess, for a few years, right? And then
Okay.
I'll let him
Yeah,
describe.
that's what I really want to see or hear, how I can
Yeah.
understand.
Well, a little background. Let you guys know I am the fifth of five stubborn sons of a southern Minnesota sodbuster, and I did not like the fact that NBOT could destroy every class of organic compound that we put against. We've dealt ballast water, we've dealt with algae, we've dealt with toxins, we've dealt with contaminants. All of them fell except PFAS, and that really irritated me that I couldn't get that one last compound. And so we started out with electrochemical oxidation. It's been reported, and it does work well, but it's an ionic mechanism. And it was sold as it's scalable. It is not truly scalable because you have to have these precious metal electrodes, and so it's a batch-oriented mechanism, and you end up with fluorinated salts, as I've shown here in the bottom. I wanted something more flow through, something that was truly scalable. As you know, Nathan, I know those are the guys are going to have gray hair by the time they're done because Austin, Texas, has to treat 600 million gallons of PFAS contaminated water daily. So we got to be able to deal with things on a much larger scale. And so I know that UV light, especially the real energetic wavelengths, about 180 to 220 nanometers, has been reported to remove fluorine as in the past, but it's slow because UV light doesn't penetrate water real well. So I combined the two. And the idea here, and it's now patented, and what we did is if you use high energy wavelengths, even if you don't break the bond, you weaken it to such a point where now hydroxy radicals can kick off the fluorine radical. And we knew this was happening because we formed fluorine
I'm
gas. That is a free radical mechanism. And so we are actually, this is a formally destructive technology. We are
okay,
stripping
okay.
fluorine.
You mentioned something, and you said something very important in what you just said that's not in the picture.
What's that?
Uh, I mean, oh, I guess it says there UV plus NBOT, I guess.
Yeah.
Okay, so you're UVing the water as well as having the nanobubbles at the same time.
Well, actually, it's a really good catch. Not really. We have to generate the nanobubbles first and then push them into the UV light. And the reason for that is that, of course, UV light breaks down ozone very quickly. And so I'm using what I've shown in this picture here is a aquaculture lamp because I nicked it from our aquaculture facility here. But we know that the reaction is happening very early in that UV light. But the advantage to nanobubbles as opposed to raw ozone is that, again, if the ozone breaks down in the presence of the UV light and it's still in the nanobubble, it breaks down to ozone. And then when the bubbles break, very quickly they can do their damage before UV light destroys it altogether. So this technology allows the nanobubble, allows ozone to have a little more time in front of the UV light, in addition to the high energy that the implosion of these nanobubbles provide. That implosion provides more hydroxy radicals than normal ozone breakdown.
Oh, I see. So the result there in the middle on the right, basically showing that two of the fluorines have been knocked off and
Right.
replaced by the hydroxy.
Correct. And we know this because that graph up there, it's tiny. I get that, but that second
I've got a
line.
bigger one here in a couple slides, Dr.
Okay,
Muller.
all right.
Yeah.
Yeah, we got 7.5 minutes left.
Oh,
Yep.
okay. I'm
I
sorry.
see
Go
that.
ahead.
No rush, but we'll use this as a template for expanding the conversation in video and
Well, yeah, well, my most important questions will come when you start talking about the application and how it affects the water. But go ahead.
Yeah. Perfect. All right, we'll move forward here. This is really just describing what Dr. Muller just described, right? But patented process, incorporating NBOT's ozonated nanobubbles into UV light with the generation of a super saturated hydroxyl radical result. But I guess to reemphasize the point that Dr. Muller is making is that UV light isn't destroying nanobubbles, is not destroying PFAS. NBOT is not by itself is not truly severing the CF bond, right? With the weakening of that CF bond, incorporating UV light enables our nanobubbles to do their work.
I understand that from what I know of breaking down of ozone with UV light, that you're talking about fairly specific wavelengths there, and I did not know that that was the same kind of wavelength that would break down, that would release the fluorine off of the PFAS. I would have thought those were two different wavelengths. Can you talk a little bit about the wavelength,
Yeah,
Peter?
well, it's 180-220. It's typical because they're such powerful, they're shorter wavelengths. It's
Right.
actually a range because every fluorine on a PFAS molecule is a little different. The bond strengths
Right.
are given in charts, but they're really average bond strengths. They vary
Okay.
whether the fluorine is terminal, whether it's inside. So you look for a bandwidth of UV light to break all of the bonds. Right now, our current bulb is using anywhere from it's about 200 to 354 nanometers because it's an aquaculture light. But I know that the stronger wavelengths are present. If I
Okay.
focused only on 180-220, I suspect we could speed this process up tremendously.
Okay. Thanks.
Yep. Getting into, I guess, really the main result that kicked off this whole body of work. Of course, this has been replicated, and we have dozens and dozens of similar style results, right? But test results from NOAA in our original round of testing proved 99.995% of true destruction, right? And in this example, started with a 3 million part per trillion PFAS concentration, obviously super hyper saturated. If I remember right, Dr. Muller, this was artificially saturated, right?
This was a
exactly.
test. Yes, sir.
And of course, something like this isn't found in nature. A lot of our testing to this point has been done in drinking water, right? We're preparing for a pilot here in the Southeast here in the coming months. Obviously dealing with much lower initial starting concentrations, but in this test started with 3 million parts per trillion. I usually present this, but Dr. Muller, this was your test, so I'll let you maybe describe
Well, it
this.
was a bit of an accident. We mixed it up, and I had a student put it together, so it's a lot higher than I would have liked. But we wanted to look for a couple of things. We wanted to see the destruction, but we had it so much in there because we wanted to see the breakdown product, so we could look at the chemistry as it went. However, we were a little bit surprised when and you look at the second graph here that's in black, as soon as we turned on the UV light, the fluorine gas came out. We're using MIMS mass spec, that's membrane infused mass spectrometry. It picked up fluorine, and the fluorine production kept on until we turned the UV light off. So we knew we were destroying, and this is the advantage to this because it doesn't care what analog of PFAS you're putting in there. It's a free radical mechanism, so you can have a 3-chain, a 5-chain, a 10-chain. Some are faster than others. I will admit that, and I can't explain that, but we haven't found one yet that isn't destroyed. Though I will say that we're going to be looking at trifluoroacetic acid here shortly.
I'm looking at this. I'm looking at this graph, of course, and look at those numbers. No, in our environment, when we're concerned about the, you know, 300, 1,000, 5,000 parts per trillion of the PFAS in our environmental water. So I'm more concerned about the right hand and the low end, and how low does it go? I mean, you said 99.995%. So even at starting with low concentrations, do you get that effect? I think that's an important question.
We do. There is a stoichiometry effect. I mean, when you really dilute your PFAS, sometimes the time can go up a little bit, but then you can adjust that with increasing the number of nanobubbles. But it right now, at least in my labs, we can we s- most of my work is at 20 parts per trillion starting, and then we see where it goes. That's a lot of the drinking water methods
Oh,
that we get,
okay.
and
Sure,
we
sure,
we
sure.
don't see a
Okay.
lot of difference.
All right,
Sure.
that was important to see. Is it good at a real low concentration?
Yeah.
Uh, that's important. Okay. And you're in the breakdown products you mentioned, but
Right
you're
right
saying,
now,
tell me,
sure,
tell me if you got another slide about that or whatever.
We got
probably not.
a little over 2 minutes, guys.
Yep.
Okay,
Yeah, I think
sorry.
we
All
timed this
right,
one well.
all right.
Go ahead,
I
Dr.
will ask my most important question then, and that is, this is strong stuff. It's gonna kills algae, so probably kills microinvertebrates, right?
Okay, you're talking about non-target species. It's a great question, and what we have found very quickly is that when we do open water tests, we cannot get ozone concentrations above about zero point 0.1 part per million. In the labs, we don't see any effect on copepods, that is the bottom of the food chain for fish, until you reach 2 parts per million in water. So we have yet to observe effects on non-target species in our open water trials.
Hmm.
Now, I'm not going to say ozone isn't doing something. I think it's like UV light does to your skin. If a molecule comes in touch with a fish gill, yeah, there's going to be, because it's indiscriminate, but there's not enough ozone there to be of significant damage.
So
That's what
what's
we've observed.
That's probably the most important question, actually, of anybody thinking about trying to do this in the environment besides a control setting where you're treating a pond of something or
Right.
uh, water that's coming out of some plant or water that's going through your water plant that you want to be nice and clean. But I really appreciate this a lot. Um, and as I say, I'm going to be on vacation. I probably won't be in a place where I'll be able to even receive a signal. I don't know. It's kind of middle of
Well,
nowhere.
guys,